So this is the first problem of today's diff 2. And in this problem, we are given that we have n sticks of length a1 to an, and we need to find the maximum number of regular, that is equal sided polygons, that can be constructed simultaneously such that each side of a polygon is formed by exactly one stick and no stick is being used more than once, like each stick is being used in only one polygon. So sticks cannot be broken. So first of all, what is a regular sided polygon? A regular sided polygon is a polygon which has all sides equal. So for example, a square is a regular sided polygon of, we can say that it has four sides. Similarly, we can say there's an equilateral triangle which is a regular polygon, all sides are equal. Similarly, a pentagon, and then there can be a hexagon. Now, there can be a triangle of unequal lengths also, like this. This is not a regular polygon. Similarly, there can be a pentagon with different sides. So something like this is also a pentagon, right? But this has unequal sides. So what we have to do, we are given some lengths and we need to find what is the maximum number of regular sided polygons that we can make. So, and by the way, we don't have to use each and every stick. We can use some sticks and we can leave other sticks. So first of all, we'll try to make a polygon which has the least number of sides, like for which we need the least number of sticks. Why? Because we're trying to be greedy. Why use, like, if we have to make a polygon of side 10 of all equivalents, we need 10 sticks. And if we actually have 10 sticks, 10 equal lengths sticks, then instead of making a one big polygon of side 10, why not make 3 triangles, right? So we just need to count like how many times each stick length is appearing. Let's say there are 3 sticks of size 5, and so for 8 length there are 7 sticks. So from these 3 we can make one triangle, and from these 7 we can make 2 triangles. So this way we just need to count how many times, like this is 3 sized sticks and this is 8 sized sticks. This is 5 sized, like 5 length sticks, and this is 8 length sticks. So we just need to count how many times each of the length sticks is appearing. Is it clear? Like this is a very easy greedy problem. Is it clear? What about others? Okay, so I'll show you the implementation. So this is the implementation. In this, I have first taken the n as input, then I have taken the array A, the array A as input, and finally I'm counting how many times each stick length is there. And for calculating answer, I'm just iterating over the counts and I'm dividing the count by 3. Why? If let's say there are 7 sticks, then I can form 2 triangles. If there are 15 sticks of some length, then I can form 5 triangles. Finally, I can print my answer. Is it clear? Okay, perfect. Why we are using a map? Because it's easier to maintain, like, count in the problem statement. Like the values are between 1 and 100, so we can use an array also, or a vector. Is it clear? How many people want me to, like, how many people have doubts in this? That, like, want me to dry run this? If many people want, then I'll do. Otherwise, I'll do this after the session. Like, if you have doubts, just write Otherwise, you don't have to write anything. How many people have doubt? Or you can raise your hand. Okay, I'll move to the next problem. So going to the next problem, we have this. So in this, we have given integers n and k. We need to construct a sequence n of n non-negative integers. That is, each value should be more than or equals to 0. And the sum of these values should be such that it is equals to k, and k is given to us in the input. Now, the number of ones in the binary representation of a1 or a2 or till like all the way up till n should be maximized. So let me explain this problem. So in this, we are given a value n and a value k. Now we have to form n values, like come up with n values such that the sum of these values, a1 plus a2 plus a3 all the way up till an is equals to k. And the OR of these a1, a2, a3 all the way up till an, this thing has maximum number of set bits. Now, one of the easiest like observations in this problem is, first in the final, let's say the final OR, we'll try to first set the minimum bit, then the next, like the lowest bit, we'll try to move from lowest significant bit to maximum significant bit. Like we'll try to set these bit one by one. And like if this bit is set in any one of these a1, a2, a3, it will be set in final OR. So we will just try to form a1 first. Like let's try to set the first bit in it. So we'll see that, okay, if we set this bit, is the total sum that we are getting. What is the sum that we're getting? We are just getting sum because of this. So 2 to the power 0. If this value is less than k or equals to k, less than equals to k, then okay. Then we'll try to set the next bit. So now 2 to the power 1. If this total is less than or equals to k, we are good to go. Then we'll try to set the next bit. So plus 2 to the power 2. If this total is less than or equals to k, again, let's continue. So like this, we'll go to a point, and after that, if we add one more bit, the total sum that we're getting here is more than k. So we'll stop here. Now we already know that only these bit can be set in the final, or if there is something remaining, we'll add it to, like we'll give the a2 that value. And by the way, it won't set any new bit because it will be something like this, like these, a combination of these bits, and they're already set. So we'll give that to a2 and the rest will be a0. But there is one corner case if we don't have a2, like let's say n is 1. So in that case, you don't have any option, but whatever is remaining, you'll have to add to a1 only, because you just need, like you have, like you need k sum and you have n equals to 1. In that case, you can just print k also. Instead of doing anything else, just you need to print k, because the final sum needs to be k and there is just one element. Is it clear? Why we are not adding the last number? We are adding, like if whatever is remaining, we like not adding it, but we are giving it to the second number. It is like kind of greedy, or I would say constructive problem. Like not bit manipulation, I won't consider this like it has something to do with bits, but we are not doing, like we are not manipulating anything. We just, if you have just the knowledge that like if like how much a bit contributes, it's more than enough for this problem. like what we are doing in this problem, if you have, let's say, n numbers, you need to form n numbers with some k. Just try to form the first number, and for the first number, let's say we'll try to set the first bit, then the second bit, then the third bit. After a point, you won't be able to set this bit because the total value of this number is more than k. So what we'll do, whatever is left, we'll give this number, let's say this value is a0, like the first value. So we'll give this as k minus a0, and all the rest will be zeros, all the remaining n minus 2 numbers. This is what we are doing. Like, any doubts? Like, other than how much rating this problem is, like if you have any genuine doubts, like you can ask me.
So when you will, like, n times, how will you represent it? Like only one times if you will subtract, can we represent it like completely?
Like, what do you mean by represent?
Like that many integers also we have to print down.
So all the remaining integers are 0. Once, like, using the first two only, we get the sum as k.
Yeah, okay.
And the remaining are zeros.
Okay, thank you.
Yeah. Any other doubts? Okay, so let me show you the implementation. So this is the implementation. In this, I have first taken n and k as input. This is my answer vector. This is my sum. Then initially, I'm like, my first element is 0. And in that element, I'm trying to set all the bits that I can. How? There is, like, please try to, like, keep yourselves muted. If you want to say something, then you can unmute yourself. So going back to this, I'm trying to, like, I'm trying to set the bits, as many bits as possible in my first number. So how I'm doing it, I know I don't have to set anything after 30. Why? Because 2 to the power 30 is more than 10 to the power 9, and k is less than or equals to 10 to the power 9. So what I've done, I have iterated from 0 to 29, and I'm checking if sum plus the value of this bit, 2 to the power I, this one left shift I is 2 to the power I. If sum plus 2 to the power I is less than or equals to k, then I'll go inside, I'll add this 2 to the power I to this sum, and I'm going to add this bit to answer, like the first number in my answer. Then after this, I'm checking that if n was more than 1, then I'm adding another 0. Otherwise, whatever is left is added to the last number. So this can be considered as, if there is just one number, the remaining is added to answer, like the first number only. Otherwise, it's added to the second number, which was 0. You don't have to do this thing. What we can do is, here only we can check if n is 1, just print k. Then you don't need to do these things. Otherwise, like what I have done here, after adding answer dot back, like after adding the remaining to answer dot back, I'm checking while my answer dot size, like while my answer vector has less than n values, I'm pushing zeros. Finally, like, forget about this. This has, like, this is just a check. So finally, what I'm doing, I'm printing my answer vector values, like each of the element in my answer vector. Is it clear? Yes, no? What about others? Like, I won't say it's a difficult problem. Like, it's not a difficult problem, but like, if you know, like, if you know how much a bit contribute, then, like, it's not a very difficult problem. No, you cannot do k minus 1 and 1. I think, like, you can come up with a solution like that. That's completely wrong. Why is it wrong? Let's say k is what can be K? Like you can come up with a solution, right? Yes, any number other than 2 to the power n, this would fail. Like there are many values of like for which this would fail. K minus 1. Like what is the reason behind this? Like you have asked this 2 times. So like why do you think this should work? Do you have any like any reason? Like why do you believe this would work? Or like just like some of like you are just asking like because you feel like it. Anyway, so this is clear, right? Is this clear to everyone? Okay, so let's move ahead. No, no, no. Like what? Okay, no, no. We no. If you have genuine doubt, I like. If you're not trying, like, if you have genuine doubt, we can discuss it right now. Like, let me explain. If you have a doubt, we can like. There is no problem. Like, I can discuss it. See, you are saying k minus 1 and 1, right? So why is this not true? Let's say you have 64 or you have 65, right? So this you'll write 64 and 1 and the rest are 0. So forget about these. Let's say what is the binary representation of this? It is 2 to the power what is this? 2 to the power 5, 6, right? 2 to the power 6. So the sixth bit I said, and these bits are 0, 1, 2, 3, 4, 5, 6. This is the binary representation of 64, and this is the binary representation of 1. So you got in final, or you'll get something like 1, 0, 0, 0, 0, 0, 1. So you have 2 bits set. But I can clearly see that there is something better. What I can do, I can set the first bit, I can set the second bit, third bit, fourth bit, fifth bit, and this bit, right? I can at least set these 5 bits, and whatever is left, what is that? This is, I think this is already 63, and you have 2 left. In the second number, you can set this thing. So binary, if you, this is 63, this is 2, everything else is 0. In the complete, in the OR, you'll get at least 5 set bits, at least 6 set bits, right? So that's why you cannot do k minus 1 and 1. Is it making sense?
Yeah, got it.
Okay, perfect. Like this is for everyone. If you have genuine doubts, you can ask. Like I won't like ignore your doubts if you have genuine doubts, and you don't have to worry like if like you're thinking like what others would think. If you have a genuine doubt, like it's possible. It is possible that others might also like learn something from that. Okay, coming back to this. So in this problem, we are given that you are given an n cross n chessboard where you and the computer take turns alternatingly to place white rooks and black rooks on the board respectively. While placing rooks, you have to ensure that no rooks attack each other. So two rooks attack each other if they share the same row or column regardless of their color. So a valid move is placing a rook on a position R comma C such that it doesn't attack any other rook. So I'll explain this in a moment. Now, what is given that we start first, and when you make a valid move in your turn, placing a rook at R comma C, the computer will mirror our move. That is, place the rook at C comma R. So I'll also explain this in a moment. The only thing is if R is equals to C, then CR will also be the same coordinate. So in that case, computer can't mirror our move and skips the turn. So we need to find, like we already have played K moves with the computer, and the computer has also like mirrored those moves. Now we must continue playing the game until there are no valid remaining moves, and we need to find how many final configurations are possible, so that like how many valid final configurations are possible after this point, like after we have played k moves and the computer has mirrored those k moves, and we need to print answer modulo 10 to the power 9 plus 7. So let me explain this first. See, what we are given, what is judgment failed in CFC problem has same issue. Like judgment fail is not probably your, like something is not wrong with your solution, but like the system was unable to judge the problem. Like, did you get this during the contest or after the contest? Okay, you got this after in system testing or after system. Okay, like, and this problem was passed during the contest. Like you got pre-test passed. Okay, some people, like not you. Okay, like anyway, I think like this would be retested later on if the judgment has been failed for some problem, some people. Like they'll probably, like the solution will be retested. Like it's not like, I don't think it's an issue with the problem, like with the solution, but it's like system was unable to process. So in this we have n cross n chessboard like this. And then we'll place some rooks. So if we decide that we are going to place our rook here, then the computer is going to mirror it. It is going to place it here. So this is mirroring. If we are placing the rook at some point, the computer is going to like just mirror it. So first of all, while mirroring, it's like not possible that the move is like not valid. Why? Can we prove it that while like it's not possible that there was a rook anywhere here? Why? Because if let's say there was a rook in this column earlier, so it simply means like let's say if there was a here, then it means that there was a rook in this row. But since we made this like move in our turn, it's not possible that there was a rook here. So it is it's not possible that there was a rook in this column. Why? Because there was not a rook in this row. Similarly, there cannot be a rook in this row earlier. Why? Because there was no rook in this column, because we made a move. See, this is the chessboard, right? So we made a move like this. Like try to understand this. We made a move, and since we made a move, okay, this is not going to work. Since we made a move, we know that there was nothing in this row and in this column, in this row and in this column. Since we made a move by keeping our rook here, right? So if this is true, then vice versa, this is also true, that there is no rook in first row, so first column, there is no rook here and there is no rook here. Why? Because this simply means that in our move there was no rook at first row, third column. So technically there shouldn't be any rook at third row, first column, because if there is a rook at third row, first column, then there is also a rook at first row, third column. Like you try to understand that no rook is at first row, complete first row, not 1,3. Like I should write it as one first row, third column. Right? So this means that there is no rook in third row and first column. Because if there was any rook in third row, then there would have been a rook in third column. If there is a rook at first column, then there would have been a rook at first row, because whatever move we make, computer is just mirroring it. Is that making sense? Like, this should be clear to everyone. If any doubt is there, let me, like, I'll explain again. Anyone having any doubts? Because whatever I'll do after this, it won't be clear if this thing is not clear. So as long as we are making valid moves, computer will always make a valid move. Okay, no doubts, right? Just write a quick yes, no. If yes, if everything is clear. No, if you want me to repeat. Okay, I'll just briefly summarize. I said if we are making a valid move, computer will always make a valid move. Because why? If we are make a valid move such as R, C, computer is just going to place a rook at C, R. In order for this not to be valid, it means that either there is a rook at Cth row or Rth column. So if there is a rook at any of these, it would mean that our move was also not valid. Why? Because if there is a rook at Cth row, it would mean that Cth row rook would mean that there was a rook at like Cth column also. Why? Because earlier the moves were just mirroring. So if there's a rook at Cth column, how were we able to place our rook at R, C? Similarly, if there's a rook at Rth row, it would mean Rth column. If there's a rook at Rth column, and why is there is a rook at Rth column? Because we are assuming that this is an invalid move. So if there is a rook at Rth column, it would mean that there was a rook at Rth row also, because moves are just being mirrored. So if there is a rook at Rth row, this is not a valid move. So it just turns out that if we are making a valid move, the computer will also make a valid move. Going further, now let's look at how these moves are actually, how many moves can at max be played? Any idea? How many valid moves can there be? There can be at max n moves. Why n by 2? Like a total number of moves, not just like one person's move. Total number of moves will be n. Why? Once you place a rook, its row and column are no more valid. And in every move, one row and one column will get, you can say, disbarred or eliminated, and there are total of n rows, right? N rows and n columns. So now what we have to do, we just need to see that some of the places have already been marked. If there is a rook placed at some R, C, and R is not equals to C, then how many rows? Like, let's forget about like one row and one column, right? So let's look only at rows, forget about columns, because it's just same. So there are n rows and each row is occupying one row. Like each row is getting, like you can say each row is disbarring one row. Each move is disbarring one row. So let's say this is the chess and we made a move such that R is not equals to C. So how many rows are getting disbarred? How many rows are getting disbarred? Can anyone? In this case, 2 rows. Why? Because R is not equals to C. We made a move as R, C. The computer will make a move as C, R. And since R is not equals to C, these both are different rows. So if there are 2 different rows, 2 rows got disbarred. And otherwise, if R is equals to C, then how many rows are getting disbarred? 1. Why? Because we just made a move and the computer will not be able to make any move. So now, what have we till now? We know that each row discards one row, and let's say initially we are given that how many moves we have made. How many moves we have made? That's equals to k.
and we know what were R and C in those cases. So accordingly, we can find how many rows are left, right? What we'll do, rows are left initially. Let's say there are n rows left. We'll iterate through each of the moves that we made. If R is equals to C, then our left number of rows is decreased by 1. If R is not equals to C, then our left is decreased by 2. So finally, we'll have how many rows are left, right? Now, how to find the total number of possible configurations from here? After this is just a constructive problem, and the solution is DP. Like, forget about DP, but how can you find how to find the total possible configuration if we have some, like, let's say if we have left number of rows. Like, try to think, like, you'll be able to come up with this. Let's say we have 3 rows left. How many possible configurations are there? Like, if you have 3 rows left, there would be 3 columns left. So forget about the columns, just look at rows. Like, let's, okay, like, if you have 3, rows left, let's say you have this one left, this one left, and this one left, this thing, and this thing left. Everything else is occupied. So this one is occupied, and this is also occupied. So if this row is occupied, this complete row will be occupied. This complete row will be occupied. And there is, this thing is gone. Okay, I have not n cross n, right? 1, 2, 3, 4, 5, 6. But this will help you in visualizing what we are actually doing. This is also not a possibility. And we have this row, this column is also not a possibility. And this column is also not a possibility. Now tell me, like, there are 3 rows left and 3 columns left. Now you can see, like, these, right? So now tell me how, like, what if you choose one row? Then what will you do? See, if you have just one left, then how many possibilities there are? If you have just one row left, there is just one possibility. One row, one cell. If you have 2, then what? You have 2 rows left, then what? How 4? How 4? Like, if you have 2 rows left, then 2 ways. How to? If you have two rows left, how can you come up with 2 ways? Can you tell me? See, you can place your rook here, and accordingly, the computer will, let's draw it. You can place your rook here, computer will place it here. You can place your rook here, computer will place it here. And what else? White will be once in first row, then second. Is there anything else? How, like, can you explain how 3 is actually right? Like, but how?
Yes, am I audible?
Yes, you are audible. Yes, you are audible.
So, like you have made a grid of 2 cross 2, right?
Yes.
So, what actually happens is when you are selecting a diagonal, so diagonal has a coordinate like II,
Yes.
and whenever I'll be selecting a diagonal, the other person will not be able to make a move.
Perfect. Perfect. So, see, the only thing that you'll have to look is this cell is 1, 1, this cell is 2, 2. So, if you keep your rook here, computer cannot make a move. If you keep your rook here, computer cannot make a move. If you keep your rook here, computer will make a move. If you keep your rook here, computer will make a move. So this is basically, in these cases, it's the same. In these cases, it's just like your rook is there. So one move, second move, third move. So there are 3 moves. Is it making sense? Like if you're able to understand this much, after this point, it's just simple. For 2, it will be 3. Is it making sense? For 1, everybody knows it's 1. For 2, it will be 3. Now try to look at for 3. I know what it will be. For 3, it will be simply like any guess. I'll also tell you the formula, but any guess? Like by how 13? Like don't guess it like by guessing. I don't mean that you just enter like give me a number. Like try to think. Like I don't mean like by guessing. I mean that try to think for a number. Like try to come up with a number. Don't like just simply enter 13. So let's see. Like I'm not going to draw it, but see, the formula for this is 2 times the number of ways you got for I minus 1. I'll explain how I minus 2. Like I'll explain how we come up for this and all the previous ways. So the previous ways for, and you need to multiply this 2 times. Like I'll explain this how I minus 1. Like what does this mean? Plus I minus 1. So this is basically the ways up till I minus 1. And in this, we are adding this much. So yes, 2 is for R comma C or C comma R. Yes. So if we have if we can place a rook at R comma C, we can also place it at C comma R. And I minus 1, why is I minus 1? Why I minus 1? Like if we have 3, see, why I minus 1? If we have 3, like okay, let's calculate first this full, like we'll know what is the right value. I minus 1. So 2 into 2 ways of 3 minus 2, 1 plus ways of I minus 1. So ways of I minus 1, ways up till I minus 1 was 3. So 2 2s are 4, 4 into 1 plus 3. So this is 7. How many got this right? And we can check this for 2 also, like not for 2 because I minus 2 is 0 in that case. Like we can, if we assume this to be 1, then we can check 2 plus 1. Like if we consider ways of I minus 2, that is ways of 0, ways, number of ways, if we have 0 rows, if we consider this as 1, then we can get the answer for 2 also from this. How? 2 into 2 minus 1, like my I is 2, into ways of 0 plus ways of 1. So we already know ways of 1 is 1, ways of 0, we have considered it 1, 2 minus 1 is 1 into 2. What is this? 2 plus 1, 3. So this formula is that way also correct. So what was I explaining? What? Yes. So you get 7 for 3, and now this way we can calculate ways for every n. Like if there are n rows left, you can get for n rows how many different configurations are possible. And I was saying that how, like, what is this? This is basically a DP question. DP of I, like how to get this. DP of ith state depends on 2 times I minus 1 into DP of I minus 2 plus DP of I minus 1. Now, first of all, is DP covered in like your levels? Like how many people are actually aware of DP here? Like what is a state and what is a transition? Okay, it's going on level 4. So probably I think only those people will be able to understand. So this is the transition from I minus 1 and I, like we are combining 2 states to get the ith state. And how we are doing this? Basically all the ways up till I minus 1 will be included in I also, like all those ways, different configurations, right? If you had only I rows, what we are doing, we only have now one more extra row. We can do this with combinatorics also. Yes, of course. Like there is, like it would be like you'll have to count factorials, and you have to, like, not factorials, you'll have to find combinations. It's like something like NCR, and that would be multiplied by 2 to the power n by 2. I'm not going to explain that here because like explaining that would require another 30 minutes, and I have already given time to this. Like that needs a separate understanding than this, like all of these things. So that's why. But if you want, you can like raise a query and ping me in it. I'll explain that also. So, and by the way, I think the intended solution for this would be DP only, not combinatorics. Like we can do it, of course, but like it's a little bit difficult and not intuitive, that much intuitive. So yes, this is like, these are previous ways only, like DPI minus 1. So in up till DPI minus 1, whatever rows were done, so we have added it, and like these were previous ways, and now we have just one more row. And we can say that one more column also. So 2 is for basically that row and column, right? And in that row, if we are having an ith row added, there would be one R comma C probably. Otherwise, we have 2 options for everything, right? Yes, no? Like for like doing it for 4 rows will be like very difficult, because first of all, like finding all the combinations, like writing the 7 combination for 3 rows is also difficult. For 3, I can explain. Yes, like it would be again 3 for 3. Like if you see, like okay, yeah, still like that is like basically this is how I wrote this DP equation, that up for getting the ith, like how many, if we have ith rows, I rows left, how would we, how many configurations are there possible? So DP of I minus 1 is just previous, 2 is for R comma C, I minus 2 and I minus 1. So I minus 2 is up till I minus 2, whatever was there. And why I minus 2? Because let's say up till I minus 2, after I minus 2, there are 2 rows added or 2 columns added, right? Yes, no? From I minus 2 to I. Yes, no, anything? Okay, so if we draw this, we'll have something like,
Excuse me, sorry.
yes,
Fran.
yes.
So we have 1 2 I rows, right?
Yes,
So you just remove 2 rows. So that can be 1 comma 2 or say anything. So that
yes,
can be written in I minus 1 ways. Is it
yes,
that logic?
yes. I'm explaining that. Yes, but you are right.
Yeah.
Can we ping you in a query? Yes, you can ping me in a query. Like you can just search Ankit, and I think there is right now only one mentor with that name. Like if, by the way, if you're not able to understand it here and you want me to separately explain you this, like probably in Hindi or anything, you can raise a query and we can come on a call. Like we'll have a call. So like I was explaining, there are two rows like this, like student also said, there are two rows and the number of ways to write, like have a hook there is I minus 1 ways. So that's why, and R comma C and C comma R 2. So that's why 2 into I minus 1 and up till whatever was, since we have removed 2 rows, I minus 2 and all the previous that were up to I minus 1. I think since see DP solutions is basically like once you write on your own, there is just one equation, but understanding that one equation is very difficult unless you have a hunch for it. So let me once show you the equation here. So what I have done, like the solution is very small, but what I have done, I have declared this outside this. I don't have to actually include 3 also. Like I have, this is how we initialize our DP. Then for every test case, I'm taking nk and nk as input. Initially, this is the number of rows that are left. Then I'm iterating through all the k moves that I have done. If x is equals to y, then I'm decreasing my number of rows left by 1. Otherwise, I'm decreasing my number of rows by 2. I'm printing whatever the configurations were possible for these many number of rows left. And how, what I have done, initially I have just pre-calculated it. How? dp of I is just dp of I minus 1 plus this thing. So 2 times number of ways to make your move and multiply with I minus 2. The number of rows between I minus 2 and I is 2. So that's why total number of ways here is I minus 1. Multiply it with this. And one thing that you need to make sure, you need to take modulo here also. I got a wrong summation because of this. You need to take modulo here. Why here? Because like not here actually, but if you're not taking modulo here, this complete thing can overflow. And since I have taken integer, not long, we have like you have to take modulo here as well as here. If you're taking this as long, you don't have to take modulo. Like you can just take modulo here. So that's it. And by the way, if you are tagging me in a query, like do share your submissions also if you have doubts regarding your submission. Like I'll just have a look, like before coming on call, I can have a look at your implementation, or like if you have some implementation or some submission, some solution on your mind, you can write that also. Yes, there is that way also, like you can derive that. Like I said, DP solution is basically if you're able to derive it yourself, then like it seems feasible, but like plausible. And yes, that is achievable using that thing also. Like if you look at diagonals. No, I won't be able, like we won't be discussing D today. And let me stop the recording.